Okay, so now what we are going to look at is a special category of directed graph. It's called a directed acyclic graph. So as the name itself indicates, so a directed acyclic graph is a directed graph without any cycle. So you all know what a cycle means by now. A cycle means you have some subset of vertices, or even all the vertices put together. You can start from one vertex and go around and come back to the starting vertex. So if you have some sequence of edges like that, then we can say the graph as a cycle. So like in this case, the second case. So start from A, go to B, go to D, go to C, and you can come back to A. So A, B, D, C, A. That's a cycle because you can start from A and come back to A. That also means you can start from C, go to A, B, D, C, and come back to C. So in a cycle, basically you can start from any vertex in the cycle and go around and come back to that vertex, because this is a cycle. You can do that for any vertex. Now there could be more than one cycle in this graph, so there's another cycle, just A, B, A, D, C. So start from A, go to D, then to C, come back to A. So A, D, C is also a cycle. So this directed graph has at least one cycle. Okay. Now let us look at this one, the first one. So whatever you try in this directed graph, you will not be able to figure out any cycle. So let us say A, D, then you cannot have any cycle. A, B, D, no cycle. So if a directed graph does not have any cycle, it is called a directed acyclic graph. So we'll shortly call it as a DAG. Okay. So now what we are going to do is, given a directed graph, use depth first search to decide whether the directed graph is a directed acyclic graph or not. So that's what we are going to find out. And after that, based on the result of that, we can proceed further, okay, to another application. So again, let us check this directed graph and we'll run depth first search in it. So we'll start with the lower alphabet A. So you push A to the stack. So A is the first vertex to be pushed to the stack. So from A we can go to one of its outgoing neighbors, either B, E or F. So we break the time by going to B. So B is visited for the first time, so we'll call the edge to B as a tree edge. So we push B to the stack. So here I'm keeping track of the push and pop orders in the stack. So B is the second vertex to be pushed to the stack, and is also on the top of the stack now. So you try to go to one of the outgoing neighbors of B, which are either F or G. So you break the time by going to the lower alphabet vertex F. So F is pushed to the stack because it's visited for the first time. So F is the third vertex to be pushed to the stack. We call the edge from B to F as a tree edge because that's used to visit a vertex for the first time. So now you are at F, from where you cannot go anywhere else because there's no outgoing edge from F. So it's time to pop out F from the stack. So F is the first vertex to be popped out of the stack. So now what we do is, the top of the stack is B. So from B we try to go to the other outgoing neighbor, which is G. Now G has not been yet visited, so we push G to the stack. So G is the fourth vertex to be pushed to the stack. From G, so again we call this edge BG as a tree edge because G is visited for the first time. Now you have an outgoing edge from G to H. Again, H has not been yet visited, so we push H to the stack and then call this edge GH as a tree edge. Now from H we cannot go anywhere else, so it's time to pop out H. So H is the second vertex to be popped out of the stack. So now we are back to G at the top of the stack. Now again we cannot go anywhere else from G, we'll pop out G. It's the third vertex to be popped out. So now we are back to B. Remember, I started with A, B, went to F and then popped out F and came back to B at the top of stack and then went to G and H. So now we are back to B at the top of the stack, but again from B we cannot go anywhere else, so we'll pop out B. That's the fourth vertex to be popped out. So now back to A at the top of the stack. Now from A, or at A, you have two outgoing edges, one going to E and one going to F. Now you could visit them in any order, but let us just break the tie by going to the lower ID neighbor E. So we'll visit E. So E is now pushed to the stack, so that is now the sixth vertex to be pushed to the stack. And so now the top of stack is E. Now you see this edge that goes from E to F. Both E and F are visited in the current instance of breadth first search, because we really started the depth first search from A and still A in the stack. We went around and came back to A. So we visited E and F in the current instance, and F is a vertex that has been already pushed as well as popped out of the stack. So we should call this edge EF as a forward edge. Okay, because F has been visited in the same instance of E and F is already pushed and popped out. So now we are back to E, still at E, so you cannot go anywhere else, so we pop out E. So now back to A. Now this edge to F again is an edge where F and A are visited in the current instance of breadth first search, and F has been already pushed as well as popped out of the stack. So we call that edge AF as a forward edge. Now we cannot do anything else at A, we cannot go anywhere else from A. So it's time to pop out A also. So A is the sixth vertex to be popped out of the stack. Now if you notice, stack is now empty because you started with A, went to B, F, and then popped out F, went to A, B, G, H, popped out H, G, and B, and back to A, went to E, then popped out E and back to A, and we cannot go anywhere else from A. So A is the only vertex in the stack, so when we pop A out of the stack becomes empty. So that means C and D have not yet been visited. So when you started this depth first search from A, you are able to visit only A, B, E, F, G, and H, and C and D are not yet visited. So we'll have to start a new instance of depth first search from C or D, one of the two vertices. So we break the tie by using the lower alphabet ID. So we'll start from C, push C to the stack. C is now the seventh vertex to be pushed to the stack. Now you have an edge that goes from C to D. So D has not been yet visited so far. So we'll call that edge from C to D as a tree edge. So push D to the stack, that's the eighth vertex to be pushed to the stack. So now from D, you have an edge to H. Now H is a vertex that has been visited in an earlier instance of depth first search, not in the current instance of depth first search that we just started with C. The current instance we visited only C and D, but in the earlier instance of depth first search we visited A, B, E, F, G, and H. So we should call this edge from D to H as a cross edge, because it's really crossing between the two different instances of depth first search. So of course H has been visited already, so we cannot push H, so we are still at D. So we pop out D of the stack. So D is the seventh vertex to be popped out of the stack. So back to C at the top of the stack. Now we have an edge to G. Again, G is a vertex that was visited in an earlier instance of depth first search. So we should call this edge CG as a cross edge. Now if you notice in this what we have done so far, we ran depth first search and classified the edges as tree edge, back edge, cross edge, forward edge according to the case, and so let's identify the push and pop numbers. But if you notice an interesting thing, there is no back edge. We ended up classifying an edge as either tree edge, forward edge, or cross edge, no back edge. So that means, again going back to what I said, if you encounter a back edge as part of breadth first search, then the graph is said to have a cycle. If you do not encounter a back edge as part of your depth first search process, we can say the graph does not have any cycle. So in that case, we can call this directed graph as what is called a directed acyclic graph, or what is called a DAG. Okay. Now once you classify the directed graph as a directed acyclic graph, we can also go and identify what is called the topological sort of the vertices. So a topological sort of the vertices is some listing of the vertices in a certain order, such that if there's an edge between say uv, if there's an edge from u to v in the graph, because it's a directed graph, so we have to specify the direction. So if there's an edge from u to v in the graph, u appears somewhere before v in the topological sort. So that is the definition of topological sort. Okay, so the definition of topological sort is this. And so the topological sort is really possible only for a acyclic graph. If the graph has a cycle, we cannot come up with a topological sort of the vertices. So topological sort really exists only for a directed acyclic graph. And what's the definition? For every edge u to v, the u should appear somewhere before v in the listing of the vertices, which is called a topological sort. So how to get the topological sort of the vertices in a directed acyclic graph? So all we have to do is now use the pop order of the vertices. So we write down the vertices in the reverse order they are popped out. So reverse order means starting from the last pop number. So the last pop number, we have 8 vertices here, so the last pop number is 8. So C is the last vertex to be popped out of the stack. So you write down starting from that last vertex popped out of the stack. So C. Then D was the 7th vertex to be popped out of the stack. So you write down D. Then A was the 6th vertex to be popped out of the stack. So you write down A. Then E was the 5th vertex to be popped out of the stack. So you write down E. Then B is the 4th vertex, then G is the 3rd vertex, then H is the 2nd vertex to be popped out, F is the first vertex to be popped out. So the reverse order of the reverse pop order basically. So the reverse order in which the vertices were popped out of the stack is called the topological sort. So here, some people may have difficulty looking at the reverse direction. So if you want to avoid making mistake, you can write the forward direction starting from the first vertex that was popped out. So F was the first vertex popped out, H was the second vertex popped out, G was the third vertex popped out. So write the forward order and just reverse that sequence. Then you get the reverse order the vertices were popped out. Or if you can right away write the reverse order, it's fine. Don't need to write the forward order all the time. So you can just write as part of your answer. Once you do that first search and find the pop order of the vertices, write down the reverse order in which the vertices were popped out. So that's called the topological sort. Okay. So again, the topological sort, the definition is, or the requirement is, a directed graph has to be a directed acyclic graph, and for every edge from u to v, u should appear somewhere before v in the topological sort. So let us go back to this graph and see if that property is satisfied. There's an edge from E to F, and you can see E appears somewhere before F. There's an edge from A to E, A appears somewhere before E. There's an edge from A to B, there's A appears somewhere before B. There's an edge from B to F, B appears somewhere before F, and so on. So you can cross check. For every directed edge in the DAG, U should appear somewhere before V. Means if you have an edge from U to V, U should appear first and V follows somewhere later. Now what is an application of topological sort? So what is the real significance of this? Now you guys know this prerequisite chart that you have to follow to take the courses. So for example, for this 228, CSE 119 is a prerequisite. So it means you have to take CSE 119 before taking CSE 228. So you can model the prerequisite hierarchy as a directed acyclic graph. So for example here, if each vertex here is a course, then in order to take F, you have to take all the three. You have to take A before taking F, you have to take B before taking F, you have to take E before taking F. Similarly, in the case of say G, you have to take both B as well as C before taking the course G. Now, such a prerequisite graph cannot have a cycle because you don't take, say, CSE1, let us say you have a sequence, CSE 118, 119 and 228. You don't take 118, 119, 228 and then you go back. That's a backage. You see the word itself, I said backage. You go back and take 118 or 119. That's not reasonable, right? So a prerequisite graph is a data acyclic graph. So now if you want to decide in what sequence you have to take the courses without violating the prerequisite requirements, if you want to decide, okay, I have 8 courses to take, in what order I should take these 8 courses so that I don't violate the prerequisite requirements. So basically just run the depth first search algorithm on the data acyclic graph or the prerequisite graph and write down the reverse order in which the vertices are popped out. So this is the reverse order in which the vertices are popped out. So that means, like if you want to have a course schedule, you could take C as your first course, then D. So if you are allowed to take, say, of course, without violating the prerequisite requirements, some set of courses, then you will take C first. Of course, since C has to be taken before D, there's an edge. You have to take first C and then take D. Okay. Now you could take A because there's no edge from C to A, so you could take A and C the same semester if you want to. And then again there's no edge from C to E, so you can take C and E in the same semester, but there's an edge from A to E, so you have to take A first and then take E in a later semester, and so on. So you see this, if you follow the sequence of courses and then check if there's an edge between from one vertex to another vertex, then and follow the courses in this order, then you will not violate the prerequisite requirements. So that's an application of the, and you see in this case, in the case of F, you take F at the end. That means by the time you take F, you should have taken its prerequisite courses A, B and E. Okay. So this is one application of topological sort. There are a lot of applications of topological sort. Okay. If you are a business person and you want to know in what sequence you should do the activities so that you don't violate like prerequisite requirements, some requirements for certain activities, then the activity graph is a data acyclic graph, and then you run depth first search and you schedule the sequence of activities you have to do in order to accomplish your entire goal for the day. Okay, so a lot of people do that. So if you don't know in what order to do, you draw a graph that will capture what you have to do before doing certain activity. So in this case, in order before taking F, you have to take A, B, and E, and so on. So once you draw the prerequisite graph, things will become kind of listed out, and then you run depth first search and write down the reverse order in which vertices are popped out. You get a topological sort, and that will give you in what order you have to do the activities or take the courses, whatever the application is. Alright, so this will stop for today. If you have any questions, you can type or ask. Let me save this video.